very good morning. Today we are going to discuss on the topic harmonic effects and its mitigation techniques under the course titled Smart Grid Basics to Advanced Technologies. Before going into the topic, I would like to explain you all briefly the importance of power quality in electrical power systems. The term power quality is used to assess the quality of electric power supply. The quality of power can have a direct economic impact on utilities and also on their customers, especially industrial customers in the form of process interruption, equipment damage, wastage of material, production loss, sales loss and so and so. Also, power quality disturbances affect sensitive electronic devices. Therefore, it is required to maintain a good quality electric power supply. Power quality is the combination of voltage quality and current quality. It is mainly concerned with the deviation of voltage and or current waveform from the ideal expected sinusoidal waveform. There are various power quality issues and problems, and among these the important problems and their causes and methods of characterizations are listed in the table. From the table, voltage sag, swell, interruption, that is serial numbers 1 to 3 are voltage related power quality problems, whereas harmonics, notches, transients and unbalanced loads, that is serial numbers 4 to 7 are current related power quality problems. One of the important power quality problem is the presence of harmonic loads in a system. They behave in a nonlinear manner. Among them, the traditional ones are as transformers, electrical machines, furnaces and so on. In addition, the modern ones include power converter based loads such as switched mode power supplies, popularly known as SMPS, ASDs using AC-DC converters, cycloconverters, AC voltage controllers, HVDC transmission, static VAR compensators and so on. Harmonic evaluation is done in terms of percentage of total harmonic distortion, that is percentage of TSD. Theoretically, the Fourier analysis is used to calculate the percentage of TSD. However, practically we measure with power quality analyzer and obtain the harmonic spectrum. Here in this slide, to give you all an idea, we can see the power quality problem in graphical representation through simulated waveforms. In left side from figure A shows the ideal sinusoidal voltage waveform. From figure B to D, the voltage related power quality problems such as sag, swell and interruption can be observed at 0.05 seconds. On the other hand, towards the right side, the ideal sinusoidal current waveform is shown in figure A, and the current related power quality problems can be observed from figure B to F. These are captured by considering various nonlinear loads which draws different harmonic components. As we discussed already, the causes of harmonics in the electric power system are mainly due to nonlinear components including power electronics devices. These harmonics are injected back into the supply system and interact adversely on the other electrical equipments connected on the same network, notably on capacitors, transformers and motors. This causes additional losses, overheating, overloading in the devices. Moreover, the harmonic current can create interference in telecommunication circuits, sharing a common path and induce the voltage by induction or conduction. Especially 9th to 21st harmonic are disruptive to communication circuits. They also produce error in power metering, that is energy or demand metering, protection and control circuits. You can see an example in the given figure. The fundamental component of current is at 50 hertz and subsequent harmonic components of 3rd, 5th, 7th and 11th are also present. The resultant current waveform is distorted. For the sake of understanding, if we take a square wave, it will produce close to 48.3% of deviation from the ideal sinusoidal waveform, that is TSD, which is equal to 48.3%. As per the IEEE standard 5191992, the harmonics should be less than 5%. Therefore, in order to compensate the harmonics, a number of mitigation techniques are available in the literature. They are passive filters, series active filters, shunt active filters and unified power quality conditioner. These filters compensate the both voltage and current related power quality problems as per the requirement. However, each has its pros and cons. Now, let us discuss them in detail. The first one is passive filters, which may be shunt type and can be seen in figure A and B, or series type, which can be seen in figure C and D, or hybrid type, which is combination of both shunt and series. These filters consist of reactive elements such as inductors and capacitors with and without switching. In high voltage AC and DC transmission system, passive filters are much in use due to its low cost, simplicity, robust structure and reactive power compensation in most of the application at the fundamental frequency. The passive filters are extensively used in distribution systems for improving the voltage profile at the point of interconnection, power factor correction, reducing losses, neutral current compensation, load balancing and better utilization of electrical equipments. Ideally, the passive power filters can supply or observe variable or fixed reactive power locally to compensate the power quality problem in the system. Even though the passive filters are extensively used in many applications, they have the following limitations. They are not adaptable to varying system conditions due to the size and tuned frequency which cannot be altered easily. The change in system conditions will detune the filter and cause increased distortion. For an effective filter design, the overall impedance must be less than the source impedance. As a result, the large size of filter is required and causes overcompensation of the reactive power. In consideration to the above mentioned limitations, the active power filters are an important and flexible alternative to compensate voltage and current related power quality problems in the distribution systems. The concept of active filter is relatively old, but recently become popular due to advancement in power electronics and their control strategies. The active filters are mainly classified as shunt active filters, series active filter and unified power quality conditioners, I mean so called UPQC. The shunt active filter is used to mitigate current related PQ problems and is also called as distribution static compensator, whereas series active filter is used to mitigate voltage related PQ problems and is also called as dynamic voltage restorer. A single solution to mitigate both voltage and current related power quality problems is UPQC, and it is a combination of both shunt and series active filters. Now, let us consider and two ideal cases, and the first one, the utility grid has good voltage quality for operating their equipment satisfactory, and the second one is the ideal condition that the loads are not injecting any harmonic currents at all. The combination to these two conditions will provide good power quality. However, this is not valid in real scenarios. The active power filter is needed for power quality enhancement. In addition, the renewable energy sources such as solar and wind are integrated at a common DC link of active power filters as shown in the slide. Thus, the renewable energy sources fed the power to load and excess power to the grid. To compensate the energy fluctuation produced by solar and wind energy due to intermittent nature, the battery storage system is connected at same point of the DC link. As a result, the utilization factor of the converters will increase and even compensate the long voltage interruption due to presence of energy storage at the DC link. Moving to the experimental hardware setup description, here we can see the single line schematic diagram of the corresponding experimental hardware setup. It consists of two back to back voltage source converters VSCs connected through a common DC link between the utility grid and the load. The grid side converter acts as a series active filter connected through a series injection transformer, and the load side converter acts as a shunt active filter connected through an inductor. The series active filter behaves as a pure sinusoidal current source and offers a high impedance path for the load harmonics. Also, LC filter is used to eliminate the switching harmonics produced by the converter. At the same time, the shunt active filter behaves as a pure sinusoidal voltage source and offers a low impedance path for the harmonics. Therefore, the flow of harmonic current through the grid is quite blocked. Here the load fed through diode bridge rectifier is treated as a non-linear load. For microgrid utilization, the emulated renewable energy sources are connected at DC link with the DC-DC boost converters. In addition, the battery is connected to the common DC link through a bidirectional DC-DC converter. To tackle the dynamics in the renewable energy sources by charging or discharging, the DC load shown is resistive in nature and connected to a common DC link. In the proposed system, the VSC are mainly employed for the exchange of real power from the renewable energy sources to the grid. Thus, the converters operate as active filters to mitigate power quality problems with effective power flow management. An FPGA controller sends different signals from the system and generates the appropriate pulses to the converters for the desired operation. For the hardware experimental setup, the specification and values of hardware parameters are provided in the table. The utility system is 3-phase, 50 Hz and 110 volt per phase. Non-linear load is realized with uncontrolled diode bridge type rectifier connected to a RL load. Source and shunt interfacing inductance are 1 and 10 millihenry respectively. LC filter is designed with 5 millihenry and 2.5 microfarad respectively. Series transformer is rated as 1 kVA with turns ratio 1:2. DC link parameter are 325 volt and 680 microfarad. Variable RL is selected to operate in various modes of operation. FPGA controller with 20 megahertz clock frequency, 1 kilowatt solar simulator and related voltage and current parameters are listed. Battery is operated at 12 volt 65 ampere hour per unit. DC load is selected up to 300 watt. DC-DC boost as well as bidirectional converter parameters are listed. Finally, the PI tuning and P and O algorithm are given in detail. Here onwards, it is quite interesting to discuss the hardware results. In hardware results, the voltage and current parameters are captured for A phase only, and these are the scaled down sensor outputs. VSA represent grid voltage of the phase A, ISA represent the grid current of the phase A, VLA represents load voltage of the phase A, ILA represent the load current of the phase A. From the figure marked as without compensation, it can be observed that the load current contains harmonics due to nonlinear loads, and it is injected back into supply system. Therefore, the source current is also distorted and contains harmonic. For the figure with compensation, the source current is sinusoidal for the same nonlinear load conditions. It is due to injection of the counter harmonics by the shunt active filters. In this case, the performance under grid voltage fluctuations are shown clearly with nonlinear load conditions. VSE underscore A represents series injected voltage of phase A, ISH underscore A represents shunt current of phase A, VDC represent common DC link voltage, IDC 1 represent DC current of the shunt converter, IDC 2 represent DC current of the series converter. From figure A, the grid voltage is 110 volt for phase and corresponding parameters are shown without external sources at DC link. Whereas, in figure B and C, the grid voltage is considered with sag and swell conditions respectively. On the other side, the real time 3 phase voltages and currents and their harmonic spectrum is captured with 3 phase power quality analyzer. With compensation under nominal condition, the 3 phase load voltages, that is V L A B C, is around 195 volt line to line with 19.68 percentage of TSD, and the load current ILABC drawn is 0.93 ampere RMS value with 26.19% TSD. Whereas the 3 phase source voltage VSABC is around 192 volt line to line with 1.92% TSD, and source current ISABC drawn is 1.32 ampere RMS value with 3.1% TSD. In this case, the step change in load is performed without and with external source at DC link. In figure A, the load is suddenly decreased without external source at DC link. We can observe that the DC link voltage rises when load is decreased and it will take certain time to reach steady state value. Whereas, in figure B, the same condition is operated with external source at DC link and feeding excess power to the utility grid. With this, the DC link voltage is regulated smoothly due to excess energy available at DC link. During excess power fed to the utility grid, the source voltage and current are in phase opposition. Also, you can observe that in both the scenarios, the source current ISA does not have any harmonics even though load contains harmonic rich current. Figure C and D are similar cases where the load is disconnected suddenly in one of the phases that is phase A. Here the harmonic spectrum is analyzed with nonlinear load without and with external source a DC link. The external DC source is considered as a PV source and grid voltage is kept at 80 volt per phase. The nonlinear load voltage and current harmonic spectrum of phase A is shown in figure A and B respectively. It can be observed that the TSD of voltage is 19.96% and the current is of 29.68%. For figure C to D, the source voltage and current TSDs are 3.56% and 3.58% respectively as shown in the figure. This is with the compensation and without any external source at the DC link. That is, only the source is supplying power to the load as well as for the compensation. In figures E and F, for the same load condition, the external source, that is solar, is connected at DC link and excess power is fed to the utility grid. You can observe that negative current in the source side, which is minus 0.73 ampere, while feeding excess power to the utility grid. The source voltage and currents are maintaining TSD less than 5% as per the IEEE standard 519-1992. Now, moving to the unbalanced conditions, the unbalanced load once consider, that is 3-phase load is having different magnitude in each phase. So, the unbalanced rate for the given condition is 48.2%. For this condition, the compensation is verified without and with external DC source at the DC link as shown in the figures A and B. The corresponding RMS currents are tabulated in the given table. Notice here, even though the load is nonlinear and unbalanced, the active filter, that is shunt filter, inject counter harmonics and reactive power to maintain the balanced source current without any harmonic currents. Therefore, the source current is almost balanced with very less unbalanced rate of 1.2% and also capable of maintaining the TSD less than 5% as per the expected IEEE standard. Here, various test conditions of hardware setup at 110 volt per phase are considered. For the above test conditions, the various parameters such as voltage, current, power factor, real and reactive power and TSD are measured in source side, load side, series and shunt side as well as towards the DC link side. These are tabulated clearly and from the table we can observe the behavior of the proposed system under various test conditions. All the presentation that we have learned today, most of them are with reference to the following 2 articles and they are in public domain, and I suggest all of you to go through these 2 articles for better understanding on this topic. Thank you.